Okay, let's do some more examples that involve probability. Let's start with this one. Let's suppose that we roll 2 dice, and let's assume these are fair dice, so that all outcomes are equally likely. What is the probability that the sum is 7? We also want the probability that the sum is less than 6. Let's start off by writing down our sample space, or at least describing it. We've seen the sample space before. If we roll 2 fair die, what are our sample space going to be? Well, we could get 1 on the first, 1 on the second. Then we could get 1 on the first, 2 in the second, 1 in the first, 3 in the second. Does this look familiar? Keep going up to 1, 6. We could get 2 on the first, 1 on the second, 2, 2, etc. Remember this? So all the possible ordered pairs that we can get. So up to 6, 1. You're going to see this a few times, and you're going to realize you don't need to write it every time. You just need to think clearly about it and know what your sample space is and how many are in it. How many possibilities are there? There are 36 possible outcomes to this experiment. Okay, and what are they? Well, all the possible ordered pairs that we can form based on the first and the second die. And so now we want to figure out the probability that the sum is 7. I guess I'll call this part A so we can label our notes. If the sum is 7, so what's my A going to be? I want to write down everything that is in event A. So I want to write down all the ordered pairs that give me a sum of 7. So let's be systematic about it and start with 1. If I want to get a sum of 7, how do I do it starting with 1? Well, I've got to put a 6 with it. Okay, let's change the order of these. Okay, now let's move to 2. So what do I put with the 2 to get a sum of 7? 5. Change the order so we get 5, 2 as well. Now let's move to 3. What do I put with it? 4. So 3, 4, and 4, 3. Are there any other possibilities? No, we moved to 4. We've already got it. Okay. So now we want to figure out the probability. So the probability of this event occurring is, since they are all equally likely, the number of elements in A divided by the number in the sample space. Okay, how many are in here? 1, 2, 3, 4, 5, 6. There's 6 elements in here. So 6 is our numerator, 36 is our denominator, so we get 1/6. Okay, let's move on. Let's look at the probability of the sum being less than 6. Okay. If it's less than 6, so what are the possibilities for my sum? Well, is it possible to get a sum of 1? No. What's the smallest possible sum I can get with 2 dice? I could get 2, right? I can't get a sum of 1. 2 is the smallest, 12 is the largest. So 2, 3, 4, 5. Do I include the 6? No, because it says less than 6. Okay. If it said no more than 6, I would have to include it. It doesn't. So I just need to do 2, 3, 4, and 5. So let's write down our event. And we're going to take these systematically. First, we're going to get a sum of 2. How do we get it? 1, 1, and that's the only way. Now we want to get a sum of 3. So 1, 2, 2, 1. Those are the ways that I can get a sum of 3. Okay, and so now we want to figure out how to get a sum of 4. So again, being systematic, we're going to start with 1. So 1, 3, switch to order, and then 2, 2, right? And now we want to get the sum of 5. So 1, 4, switch to order, 4, 1. Then move to 2, so we get 2, 3. Switch to order, 3, 2. Make sure you put your parentheses so they're ordered pairs. Those are the only ways to get to a sum of 5. Okay, so how many are in here? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Check. 4, 5, 6, 7, 8, 9, 10. Yes, I agree there's 10. And so our probability then will be 10 over 36, or 5/18. Does that make sense? Okay, let's move on. Let's suppose that my electricity went out last night. No flashlight, had to choose a t-shirt at random, and all the t-shirts are in a particular area. And let's suppose I happen to own 10 white ones, 5 gray shirts, 6 black ones, and 2 red shirts. What is the probability that I chose a gray t-shirt? Okay, well, let's let G be the set of gray t-shirts. And so then what is our sample space? Our sample space is the set of all possible t-shirts. How many are in our sample space? Well, the 10 white ones are in there, and the 5 gray ones are in there, and the 6 black, and the 2 red, so that leaves me with 15, 21, 23 t-shirts that are possible. And how many gray ones are there? 5, right? So what is my probability that I got a gray t-shirt? Number of gray ones divided by the total number of possibilities. There's 5 gray t-shirts, 23 total. And you could come up with a decimal approximation for this if you wanted, which might make it a little more meaningful intuitively. That will be approximately 0.217. Okay. Let's do another one. Let's suppose that Joe, Steve, Susie, and Lisa all work for the same company, and they're going to pick 2 to go to a particular conference, and the other 2 have to stay home. All of them want to attend, so they do it at random, drawing 2 names out of a hat. What is the probability that both Susie and Lisa are selected? Okay, so we need to write down our sample space. And before we do that, let's come up with a little bit of shorthand for our notation so we don't have to write out all these names every time. Okay, so J will be Joe, right? That one's easy. And we'll let ST be Steve. SU is Susie. And L for Lisa. Okay, so what are the possible things that can happen here? Well, let's again be systematic. Joe happens to be listed first, so let's put him with each of the others. We could have Joe Steve. We could have Joe Susie. We could have Joe Lisa, right? Okay, now what about changing the orders? If I change the order and do Joe Lisa, would we call that a different outcome, or would we call that the same outcome? We call that the same outcome, right? In other words, here we don't care about the order. We don't have like first place, second place, like with the dice. Okay, so these are different possibilities. So that's putting Joe with everybody. Let's move on. Let's do Steve. Okay, well, we have already put him with Joe, so we don't want to list that one again. But we could have Steve with Susie. We could also have Steve with Lisa, right? And then we could have Susie with Lisa. Okay, and those look like our only possibilities. And all of these are equally likely, right? Everybody's name is in the hat only once, and so there's no reason to expect any of these to be more likely than any other one. Okay, so what is the probability that Susie and Lisa are selected? So Susie and Lisa. Okay, so probability will be the number in my set divided by the number in the sample space. How many are in my set? 1. How many are in my sample space? 1, 2, 3, 4, 5, 6. So 1/6. Okay, let's move on. Okay, let's suppose these are the tuition categories, the numbers of students in the various tuition categories in the spring of 2007. This is accurate data taken from the college website. What is the probability that a randomly selected student lives in district? Well, okay, let's think about our sample space. What's our experiment that's occurring? We are randomly selecting a student. So what are our possibilities? As all students, right? If it's really truly random, all students have an equally likely probability of being selected. Okay, well, how many are in here? Well, I would add all of these up. So take your 97, 94 plus your 428 plus your 104 plus your 250 plus your 9. Punch all of this into your calculator and see what you get. Why don't you do it along with me? Okay, I get 10,585. Okay, so what's the probability that a randomly selected student lives in district? Okay, we'll call this event A. How many are in district? 97, 94. How many total possibilities are there? 10,585. And so this fraction is, if you get a fraction of 1/3, well, that's a meaningful number. This fraction is not very meaningful. So we are going to get a decimal approximation. And you should get approximately 0.9257. Okay. What's the probability that a randomly selected student is an international student? Okay. Well, there are 250 international students divided by the total of 10,585. You should end up with a decimal between 0 and 1. If you don't, something is very wrong. And you should ask yourself if your answer seems reasonable. Mine does. In other words, about 92.5% of our students are in district. About a little over 2% are international students. That certainly seems reasonable, and it certainly seems reasonable based on the numbers that are given above. This is what we call empirical probability, meaning data were gathered instead of just using theory as we did in the problems about the dice and the coins. Okay, let's do another one. Here's some more information about the college. Okay, so what are the probabilities associated with each of these categories? If you're given a percentage, okay, you're going to use that percentage to come up with a probability. Well, what probability would be associated with let's ask it this way. What's the probability that a randomly selected student would be under 20? We'll just convert that percentage to a decimal. So you get 0.334. For this one, what will we get? 0.356, 0.113, and so on. Okay, so what's the probability that a randomly selected student is under 20? 0.334. Okay, what's the probability that a randomly selected student would be over 40? Well, let's see which categories qualify. All of these qualify, and actually over 40, this includes 40. Let's change this to 40 or older, just so that we can actually answer it based on the information that's given in the table. In other words, this will be 40 or over. Okay, so here, what do we end up with if I switch this to probabilities? 0.063. Remember, you move your decimal 2 places to the left, and then 0.020. So here, the probability of this will be 0.063 plus 0.02, which would be 0.083. Okay, what's the probability that a randomly selected student is over 60? Is there enough information in this problem to determine it? We have categories for under 20. We have categories for people 25 through 29, then in their 30s, in their 40s, 50 and over. But we don't have the 50 and overs broken down into 50s, 60s, 70s, and so on. So there is actually not enough information to answer this. However, we can get an idea. Is it possible that 30% of the students are over 60? No, because what do we know? If we look at the 50 and over category, we know that only 2% of them are 50 and over. So we do know that this probability, we don't know exactly what it is, but we know it's some of this 2%. Perhaps all of it. Perhaps there's no one between 50 and 60 and everyone is over 60. But we don't know that. But we can say that it's going to be smaller than or equal to 0.02 from this line of our table. Okay, well, I hope this helped you to learn about probability. We'll